Continuing physical chemistry, chapter 2. We're now starting chapter 2.8. We know from before that an ideal gas is one that is described by PV equals nRT. This formula makes two assumptions. One is that there are no intermolecular forces, and two, that the molecules do not occupy any volume. Now we know that average translational energy is proportional to temperature, and we denote it E. This bar means average translation, and then average vibrational energy is also proportional to temperature. And we denote that E, the bar means average, and VIB is for vibrational. And then average rotational energy is also proportional to temperature. And again, E, the bar means average, and ROT is for rotational. Now, we know that constant temperature, the derivative of U with respect to V, constant T, equals 0. Now, that's how we're going to define a perfect gas. We're going to say, for a perfect gas, 1, it's PV equals nRT, just like an ideal gas. And 2, that the derivative of internal energy with respect to volume at constant temperature is equal to 0. So we know that for any closed system, U is a function of temperature and volume. But for a perfect gas, we're just going to say that U is a function of temperature only. Okay, continuing on chapter 2.8 of physical chemistry, last time we started talking about reversible adiabatic processes for a perfect gas. We showed that temperature 2 divided by temperature 1 is equal to volume 2, or volume 1 over volume 2 to the R over CVM power. That's only true for a perfect gas, for a reversible adiabatic process, and it was assuming that heat capacity is constant. Now, remember, for an ideal gas, N and R are constants, so P1V1 over T1 is equal to P2V2 over T2. We're going to use that to change our math a little bit here. So solving for T1 or T2 over T1, then we get P2V2 over P1V1. And then we know that is equal to V1 over V2 to R over CVM. Distributing out the exponent, then we have V1 to the R over CVM divided by V2 over to the R over CVM power. Now combining what we found here with what we had here and simplifying the exponents a bit, then we have P1 V1 is to the R over CVM plus 1 power, and that's equal to pressure 2 volume 2 to the R over CVM plus 1 power. Now remember, if we have R over CVM plus 1, if we want to add this, we need a common denominator. So that gives us R plus CVM over CVM. We know that R plus CVM for an ideal gas only is CPM. So we have CPM over CVM, and we're going to define that as gamma. And no, it's not a type of radiation. So gamma, we know is CPM over CVM. That's the intensive version, but it works just the same if you have extensive quantities. We have Cp over Cv, comes out the same. Gamma is known as the heat capacity ratio. Now, we can just say for an adiabatic process that pressure 1 times volume 1 to the gamma is equal to pressure 2 times volume 2 of the gamma. Continuing on physical chemistry, chapter 2.8, we know that Cv is equal to the derivative of internal energy with respect to temperature at constant volume. For a perfect gas, there's only one variable. Therefore, we're going to say that Cv is just equal to du over dt. So we can solve for du and just get Cv dt. And Cv is a function of temperature only for a perfect gas. And remember, enthalpy is defined as U plus PV. So substituting out PV equals nRT for an ideal gas, we can say that enthalpy equals U plus nRT. But remember, both enthalpy and internal energy are functions of temperature. Likewise, the heat capacity at constant pressure is equal to the derivative of enthalpy with respect to temperature at constant pressure. Since for ideal gas, we only have one variable, then we can say that Cp is equal to the derivative of enthalpy with respect to temperature. Ordinary derivative instead of partial derivative. So solving for dH, we can say that the differential enthalpy is equal to the heat capacity at constant pressure times the differential of temperature for a perfect gas only. Now, also for a perfect gas, we know that the derivative of internal energy with respect to volume at constant temperature is equal to 0. So we also know that Cp is equal to Cp of T. In other words, heat capacity at constant pressure is a function of temperature only for a perfect gas. Now, we showed before that the heat capacity at constant pressure minus the heat capacity at constant volume is equal to the derivative of internal energy with respect to volume at constant temperature. This term is called the internal energy, or internal pressure, plus pressure, and all that times the derivative of volume with respect to temperature at constant pressure. Now, we know, because for a perfect gas, that this internal pressure term is equal to 0. Therefore, this is going to disappear, and we'll just have that. So we have Cp minus Cv is equal to pressure times the derivative of volume with respect to temperature at constant pressure. And this is only true for a perfect gas. Continuing on, physical chemistry, chapter 2.8. So we know that the derivative of internal energy with respect to volume at constant temperature is equal to 0. So we know that Cp minus Cv is equal to pressure times the derivative of volume with respect to temperature at constant pressure for a perfect gas. Now we also know perfect gas obeys PV equals nRT. So if we solve for V, we get nRT over P. So what we want to do is substitute that into this derivative. So the derivative of volume with respect to temperature at constant pressure for a perfect gas is just the derivative with respect to temperature at constant pressure of nRT over P. Now we said P is constant, so we can pull that out. N and R are constant, so we'll pull that out. So we have left just the derivative of temperature with respect to temperature, which is 1. Therefore, the derivative of volume with respect to temperature at constant pressure is just nR over P. So we have Cp minus Cv is equal to P times nR over P. The P's cancel out, so we get Cp minus Cv is just equal to nR. Remember, R is the gas constant, 8.314 joules per mole Kelvin, and N is just the quantity of particles, number of moles. So divide both sides of this equation by N, so we get Cp over N minus Cv over N is just equal to R. So what we have here is the molar heat capacity at constant pressure minus the molar heat capacity at constant volume, and subtracting those gives you R for a perfect gas. So like I just said, Cpm is the molar heat capacity at constant pressure. Cvm is the molar heat capacity at constant volume. So we have the derivative of internal energy with respect to volume at constant temperature, and that's equal to minus the heat capacity at constant volume times mu J, which is equal to 0. Well, we know the heat capacity can't be 0, therefore we know that mu sub J is equal to 0 for a perfect gas. Likewise, we know the derivative of enthalpy with respect to pressure at constant temperature is equal to minus Cp times mu Jt, and that's equal to 0. Likewise, heat capacity cannot be 0, therefore mu Jt must be equal to 0 for a perfect gas. Okay, continuing on chapter 2 of physical chemistry, we're in chapter 2.9 now. We're calculating first law quantities of different processes. Now we're going to talk about a reversible phase change, which happens at both constant temperature and constant pressure. Examples of this would be like boiling, melting, freezing, etc. Now the energy going in is called the latent heat. For example, if you're boiling it, you might call the latent heat of evaporation, or if you're melting it, you call the latent heat of melting, etc. So Q is greater than 0 if you're melting it, or likewise if you're allowing it to freeze, then Q would be less than 0. Now, this is something that thermodynamics cannot answer. Latent heat is found experimentally. Maybe later on when we get into quantum mechanics, we can come up with some of this, but not everything. Now work is going to be equal to just minus P delta V, since it's at constant pressure. And that's also going to be equal to minus nR times the integral of T over V with respect to volume. But to evaluate this integral, we would need temperature as a function of volume. Now so the change of volume is going to be proportional to both the mass and the density rho. M is mass, rho is density, remember. So let's give an example. We have solid in equilibrium with liquid. That's going to be melting or freezing, obviously. So the volume of the solid, that's going to be just the mass divided by the density of the solid. And likewise, the volume of the liquid is just going to be a mass divided by the density of the liquid. That's going to be for your extensive quantities. Now, since we're at constant pressure, of course, delta H, the enthalpy, is just going to be equal to the heat in constant pressure, QP. Likewise, the change in internal energy, delta U, is going to be equal to the change in Q, work constant pressure, plus the work done. Okay, continuing on chapter 2.8 of physical chemistry, we were talking about a perfect gas, and we showed that mu J is equal to 0, mu JT is equal to 0. And of course, you can't liquefy a perfect gas because there are no intermolecular attractions in a perfect gas. Now, let's apply the first law to this formula here. We have differential of work reversible is equal to minus PdV. This is if you have a reversible volume change. Now, we also know that du is equal to CV dt for a perfect gas. So we're going to substitute that out. We're going to say du is equal to dq plus dw. Well, that's from the definition of du, actually. So, by transitivity of equality, these two are equal. So we have Cv dt is equal to dq plus dw, or that's equal to dq minus pdv. This is true for a perfect gas, for any reversible process, doing PV work only. Now, let's figure out how we actually do some calculations for this stuff. It depends on the type of process. The first one we're going to do is a reversible isothermal process of a perfect gas. Since it's isothermal, we know that delta T equals 0. Since U is a function of temperature only for an ideal gas, we have delta U is equal to 0. Likewise, since enthalpy is a function of temperature only for an ideal gas, then we have delta H is equal to 0. Now we know that delta U is equal to Q plus W for any process, but we know that delta U is 0 for this process. So we have that Q is equal to minus W. Now remember, work is the integral from volume 1 to volume 2 of pressure with respect to volume. And we're going to use PV equals nRT to solve this. So we're going to write work reversible is equal to minus the integral from volume 1 to volume 2 of nRT over volume with respect to volume. Now we said this is a constant temperature process, so we can pull out the nRT. So we have work reversible is equal to minus nRT times the integral of V1 to V2 of 1 over V dV. The integral of 1 over x with respect to x, of course, is the natural log of x. So we have this work reversible is equal to minus nRT times the natural log of V2 over V1. We can get rid of the minus sign just by flipping that fraction upside down. So we normally write it as work is equal to nRT times the natural log of volume 1 divided by volume 2. Okay, continuing chapter 2.8 of physical chemistry, finishing up what we started about reversible isothermal process in a perfect gas. We showed that work is equal to nRT times the natural log of V1 over V2. This applies whether the gas is expanding or being compressed. Now, if V2 is greater than V1, then work is less than 0. But if V2 is less than V1, then work is greater than 0. Now, Boyle's law says that at constant temperature, P1V1 equals P2V2. This only applies to an ideal gas, obviously. So, rearranging that, we get V1 over V2 is equal to P2 over P1. Substituting that back in up here, then we have work can also be written as minus nRT times the natural log of P2 over P1. That's a constant, convenient shortcut sometimes when you're solving a problem. And again, this is only valid at constant temperature. Now, expanding on what I was saying earlier, if volume 2 is greater than volume 1, then work reversible is less than 0. So that means that our system is expanding and it's doing work. Now, that of course also means that Q has to be greater than 0. So heat is being absorbed by the system to do the work. Now we're going to talk about a reversible constant volume process in a perfect gas. Now since the differential of volume is equal to 0, and the differential of work is equal to minus P times the differential of volume, we know that the differential of work is equal to 0. It's kind of ugly 0 there. Okay. So by the first law that says du equals dq plus dw, then we know that dq is just equal to du for this process. So if q is greater than 0, we're going to warm up the system. So delta T will be greater than 0. And for a perfect gas, U is a function of temperature only, so delta U will be greater than 0. Now remember, du is also equal to Cv dt for a perfect gas. Continuing on physical chemistry, chapter 2.8, now we're going to talk about a reversible isocoric process. Isocoric means constant volume, of course. So the change in enthalpy is going to be equal to the integral from T1 to T2 of Cp dt, and the change in internal energy is going to be equal to the integral from T1 to T2 of Cv dt. And remember, molar CPM, the molar heat capacity constant pressure minus the molar heat capacity constant volume is equal to R for a perfect gas. Now let's talk about a reversible constant pressure process, for a perfect gas, of course. We know that the differential of work reversible is equal to minus PdV. So we know that the work reversible is equal to minus P times the definite integral from volume 1 to volume 2 of dV, which is equal to minus pressure times the difference in volume, V2 minus V1. We also know that dQp is equal to Cp dt, therefore Qp is equal to the integral of Cp dt. Now we know delta H is equal to Qp. This is very important to remember for a constant pressure process. And delta U is just going to be equal to Q plus W. Now what about a reversible adiabatic process for a perfect gas? Well, we know that Q is equal to 0, therefore delta U is equal to work. And so we know the Cv dt is equal to minus PdV, and therefore, thanks to the ideal gas law, Cv dt is equal to minus nRT over volume times the differential volume. Now we're going to divide both sides by m, so we're going to get the molar heat capacity dt is equal to minus RT over V times the differential of volume. Now we're going to integrate both sides of this. So we have the integral from state 1 to state 2 of the molar heat capacity at constant volume divided by temperature with respect to temperature. It's going to be equal to minus R times the definite integral from state 1 to state 2 of 1 over volume times the differential of volume, or with respect to volume. Now remember, looking at this part only here, that's going to be minus natural log of V2 minus natural log of V1 can also be written as just R of natural log of V1 over V2. So that's for this integral. Continuing physical chemistry, chapter 2.8. Now we're going to actually calculate the what happens in different processes. We're going to start with a reversible isothermal process for a perfect gas. Remember, isothermal means constant temperature. So delta T is equal to 0. And we've shown before that internal energy U is a function of temperature only for a perfect gas. Therefore, we know that the change in internal energy is also equal to 0. We also know from the first law of thermodynamics that the heat plus the work is equal to the change in U, internal energy. Therefore, Q plus W is equal to 0 for this process. So getting those apart, we just end up as the Q heat is equal to minus the work. Now, we also know from the definition of work that it's equal to the, since dW is equal to PdV, integrating that, we get work is equal to minus the integral from volume 1 to volume 2 of pressure with respect to volume. Solving, or actually using PV equals nRT then, we're going to have the integral from volume 1 to volume 2 of nRT over volume with respect to volume. nRT are constants because we said constant temperature, so we just end up with work is equal to nRT times the integral from volume 1 to volume 2 of 1 over volume with respect to volume. Hopefully you remember from calculus that comes out to the natural log. So we get work is equal to minus nRT natural log of V2 over V1. If we flip this fraction upside down, it becomes negative. Double negative makes a positive. So work is equal to nRT times the natural log of volume 2 over volume 1. And this will apply whether your system is expanding or compressing. It works out the same either way. Now, if the volume at state 2 is greater than the volume at state 1, then the work reversible is negative. In other words, the system has done work and lost it. Well, yeah, it's done work. So that means that the energy had to come from somewhere. Since delta U was 0, that all that work being done is from heat. So we have converted heat to work. And vice versa, if the volume at state 2 is less than the volume at state 1, then work is greater than 0, which means we compress the system, and of course then heat must have come out. Q is less than 0. Now remember, Boyle's law says that at constant temperature that pressure 1 times volume 1 is equal to pressure 2 times volume 2. So if we rearrange that a little bit, we get V1 over V2 is equal to P2 over P1. We can substitute back into our equation here, and then we get work is equal to nRT natural log of pressure 2 over pressure 1. But this is only true at constant temperature, remember, and for an ideal gas. Continuing on chapter 2.8 of physical chemistry, we're talking about ways to calculate stuff for different types of processes. So now we're going to do a constant volume or isochoric process for an ideal gas. Now, by the definition, we know that V is constant, therefore the differential of V is equal to 0. Remember that we defined the differential of work, dW, as minus PdV, which we know is 0, therefore dW is equal to 0 also. We also know from the first law that du is equal to dq plus dW. Since dW is 0, now we have du is just equal to dq. Now, if Q is greater than 0, which means heat is coming into the system, then the system is going to warm up. The temperature is going to increase. We'll use du is equal to Cv dt to calculate that. And of course, delta U will be greater than 0 since we're adding heat energy to the system. Now remember the difference between enthalpy and internal energy. Enthalpy is at constant pressure, and internal energy is at constant volume. So we're going to calculate the change in enthalpy as the integral from temperature 1 to temperature 2 of the heat capacity at constant pressure with respect to temperature. And likewise, we'll calculate the change in internal energy by calculating the integral from temperature 1 to temperature 2 of the heat capacity at constant volume with respect to temperature. And if you're given only one of those two, just remember that the molar heat capacity at constant pressure minus the molar heat capacity at constant volume is equal to R for a perfect gas. Continuing on physical chemistry, chapter 2.8, we're talking about different ways to calculate different types of processes. Now we're going to do a constant pressure isobaric process for a perfect gas. Now we know from the definition that the differential reversible work is equal to minus PdV. So we integrate that to get the total reversible work. It's constant pressure, so we can pull that out of the integral. So we get minus P times the integral from volume 1 to volume 2 with respect to volume. And then, of course, that just becomes the change in volume, volume 2 minus volume 1. Likewise, we know that the differential of heat at constant pressure is just equal to the heat capacity at constant pressure with respect to temperature. So we're going to just integrate both sides to get QP is equal to the integral of Cp dt. And at constant pressure, then we know that the change in enthalpy is just the heat at constant pressure. And likewise, we know from the first law that the change in internal energy U is just equal to the heat plus the work. Continuing on chapter 2.8, we're calculating different stuff for types of processes. So number 4, we're doing a reversible adiabatic process for perfect gas. Remember the definition of adiabatic, Q is equal to 0. And we know that delta U is equal to Q plus W. So if Q is 0, delta U is just equal to the work done. We also know, remember, that delta U is equal to Cv dt. and work is equal to minus PdV. So that we're going to take PV equals nRT and substitute out this P. So we're going to get CV dt is equal to minus nRT over V dV. We're going to divide that by n to get the intensive form. So we're going to end up with the heat capacity constant volume intensive times the differential of T is equal to minus RT over V times the differential of V. Now we're going to integrate that now that we have, we're going to integrate that. So the integral from state 1 to state 2, oh yeah, we got T over on this side because we need to integrate with respect to T. That's what I was going to say. So we're going to integrate CV over M over T with respect to T, and that's going to be equal to R times the integral from state 1 to state 2 of 1 over V dV. Now we know that the integral of this will be just natural log. So remember, R is constant, we pulled that out already. So we get minus R is equal to natural log of V2 minus V1, which can be rewritten as just R times the natural log of V1 over V2. We showed that last slide. Likewise, integrating this side, CVM we're assuming constant, so we're going to integrate 1 over T dt, that's natural log. So we end up with CVM times natural log of T2 minus T1. And again, it's shorter to just write as a fraction. So we have CVM times the natural log of T2 over T1. So these two, of course, are still equal to each other. So we have CVM times the natural log of T2 over T1 is equal to R natural log of V1 over V2. We're going to divide that by CVM, so we get the constants over on this side. So we're going to get natural log of T2 over T1 is equal to R over CVM, which is the natural log of V1 over V2. Which, remember, for natural logs, we can put this out here as an exponent. So we have natural log of V2 over V1 to the R over CVM power. Make sure these units, you use the same units. Obviously, to take an exponent, you need a dimensionless quantity. Now, we're going to take the natural number e to both sides, take e to both side power, basically. So we're going to end up with just T2 over T1 is equal to V1 over V2 to the R over CVM power. So if volume 2 is greater than volume 1, obviously our system is expanding, which means for an ideal gas, temperature 2 will be less than temperature 1. Our gas is going to cool. Continuing on chapter 2 of physical chemistry, we're finishing up chapter 2.8, continuing what we said about adiabatic processes. So we know that delta U is equal to the integral from temperature 1 to temperature 2 of CV dt. So for an adiabatic process, Q is equal to 0. So delta U is just equal to the work done. Enthalpy, of course, is the integral from T1 to T2 of Cp dt, which would be just Cp times delta T. Now let's say we do an expansion from volume 1 to volume 2, starting at pressure 1. If we do it as an isothermal process, we're going to end up with different results than an adiabatic process. The reason is because with an isothermal process, we'd be putting some heat into the system, and with the adiabatic, we're not putting any heat into the system. Since the adiabatic process is going to end up with lower temperature than the isothermal process, then obviously the adiabatic process is going to end up with lower pressure than the isothermal process too. Also, one other trick that you might find handy, delta H enthalpy is equal to delta U plus delta PV. Since for an ideal gas, perfect gas, PV is equal to nRT, so we could just say that the change in enthalpy is the change in internal energy plus nR times the change in temperature. Continuing on chapter 2 of physical chemistry, we're now just starting chapter 2.9. In chapter 2.9, we're going to show how to calculate the first law quantities of a whole bunch of different types of processes. First law quantities include the change in enthalpy, the change in internal energy, the heat, and the work. Now the easiest one is probably the cyclic process. Remember, we said a cyclic process is any process in which you end up in the exact same state that you started with. What that means is that any state function is going to be exactly where it started with. So that the change in any state function is going to be 0 for a cyclic process. Now, so far the state functions we've covered are enthalpy, so delta H is equal to 0. temperature, so delta T is equal to 0, volume, so delta V is equal to 0, pressure, so delta P is equal to 0, and of course internal energy, so delta U is equal to 0. Now on the other hand, Q and W are not state functions. So for a cyclic process, Q is not necessarily equal to 0. In fact, it's probably not. There's no point in having the process in the first place. And likewise, work will probably not be equal to 0. Otherwise, the process doesn't really accomplish anything. Now, as far as notation, this integral symbol with the circle means cyclic integral. So if we have a state function, the cyclic integral of this u du for any state function is going to be equal to 0. On the other hand, if you do a cyclic integral of something that's not a state function, such as dq, that's not going to be equal to 0. Continuing on physical chemistry, chapter 2.9, we're calculating first law quantities for different types of processes. Now we're going to talk about a constant pressure heating with no phase change. Now we know that work, we're always talking about reversible work, is equal to minus integral from state 1 to state 2 of p dv. At constant pressure, you just pull the p out, and the integral of dv just becomes delta v. Now, how to find delta v could be tricky, of course. It depends on if you're dealing with a condensed phase or the gaseous phase. If you're using the condensed phase, you might have densities. For example, the change in volume will be proportional to the mass over density. On the other hand, if you have the gaseous phase, then you'll probably end up, if it's an ideal gas, just use PV equals nRT to find your change in density for this process. Now enthalpy, of course, we know, since we're at constant pressure, is QP, or another way to find that would be the integral from temperature 1 to temperature 2 of C of P dt. Remember, C at constant pressure could be dependent on temperature. If it's constant, that's going to be easy enough, you'll just pull it out. But if it's not constant, you might have it in the form of an equation, such as A plus BT, but likely A and B would at least be constants, so integration would be manageable. Delta U we know is going to be QP plus W, just like we saw last time. And these formulas, they're actually going to work not just for constant pressure process, but any process where the final pressure is equal to the initial pressure. Okay, we're continuing physical chemistry, chapter 2.9. We're calculating first law quantities for different processes. So the fourth process we're going to look at is the constant volume or isocoric process. And we're going to be heating it by cooling, whatever. And we're assuming no phase change because that would be extra step. We already covered it anyway. So we know constant volume means delta V is equal to 0. And we know that the differential of work is equal to minus PdV. Therefore, the work must be equal to 0 for this process. Since, based on the first law, then, we know that delta U is just equal to heat at constant volume. Now, we also have delta U is going to be equal to the integral from state 1 to state 2 of heat capacity, constant volume, with respect to temperature. So that, we already said, is equal to the heat at constant volume. So obviously, we're going to need the heat capacity at constant volume if we're going to find delta U that way. Now, we also know that delta H, enthalpy, is going to be delta U plus delta PV. Since it's constant volume, we can just pull that out and say delta U is equal to V delta P. And of course, if we have a perfect gas, you might be able to find it the other way, saying delta H is equal to delta U plus nRT delta T. Continuing on physical chemistry, chapter 2.9, we're calculating first law quantities for various processes. Now we're going to talk about a change of state in a perfect gas. So we're going from temperature 1 and volume 1 to temperature 2 and volume 2. Now we know that the differential of internal energy is equal to C constant volume dt. So delta U is just going to be the integral from temperature 1 to temperature 2 of heat capacity with respect to temperature. Likewise, we know that the differential of enthalpy is equal to C at constant pressure dt. So finding delta H is just going to be the integral from temperature 1 to temperature 2 of C of P dt. Now the work we know is defined as minus PdV. So that's going to be equal to minus nR times the integral of t over v with respect to v. The obvious problem is, though, that this is path dependent. We need to know temperature as a function of volume, because temperature is not constant. We can't just pull it out, and we can't integrate with respect to t. We're integrating with respect to volume. So we would need some sort of equation of state. Of course, for an ideal gas, you could just substitute that in that way again. No, that would be more. Anyway, Q is equal to delta U minus W. Okay, continuing on, chapter 2.9 of physical chemistry, we're calculating physical law quantities of different processes. We're going to talk about reversible isothermal processes now for a perfect gas. We already did that last section. I'm just going to add a couple things here. So we know T is equal to constant. Well, T is constant, therefore delta T is equal to 0. We know that internal energy U is a function of temperature only for a perfect gas. Therefore, delta U is going to be equal to 0. We also know that for a perfect gas, enthalpy is a function of temperature only. Since delta T is equal to 0, then delta H will also be equal to 0. Now we know that work is equal to minus the integral from state 1 to state 2 of pressure with respect to volume. Using the ideal gas law, then, it's equal to minus nRT natural log of V2 over V1. Or getting rid of the minus sign, we get nRT's natural log V1 over V2. Or using Boyle's law, I showed you that before, how to do that. Work is equal to nRT natural log of pressure 2 over pressure 1. And then, of course, Q will be equal to minus W. Continuing on physical chemistry, chapter 2.9, we're calculating first law quantities for different types of processes. Number 7, we're going to do a reversible adiabatic process. We already did the derivations in the last sections, but just to summarize, we know that Q is equal to 0 because that's the definition of adiabatic, which leaves us that with delta U is just equal to W. Actually finding that, you might then have the integral of from temperature 1 to temperature 2 of C constant volume with respect to temperature. Or the change in enthalpy would be the integral also from temperature 1 to temperature 2, but of the heat capacity at constant pressure with respect to temperature. That gave us this equation. The temperature 2 over temperature 1 is equal to volume 1 over volume 2 to the R over CV m power. Another way to write that would be P1 V1 to the gamma is equal to P2 V2 to the gamma. And we defined gamma as the heat capacity at constant pressure divided by the heat capacity at constant volume. Okay, physical chemistry, continuing chapter 2, finishing up section 2.9. We're calculating first law quantities for different types of processes. This time we're doing an adiabatic expansion of a perfect gas into a vacuum, also known as free expansion. Hopefully you remember this from before when we talked about the Joule experiment. This is the Joule experiment. Now we know it, since it's adiabatic, the Q equals 0. And remember we showed that work is equal to 0 because there's no external pressure. So for the first law, we can calculate that delta U is equal to 0. Now we know that delta H is equal to delta U plus delta PV. For an ideal gas, then, delta H is equal to delta U plus NR delta T. Now we know that delta T is equal to 0 for this process, and U is equal to U of T. So this is another way we can confirm that delta U is equal to 0. So plugging all that back in, then we also know that this experiment is also actually constant enthalpy. Delta H is equal to 0.